Hey guys, today we are going to be finding the real zeros of a polynomial. So we're going to be finding all of the possible real solutions to a polynomial, and we're going to use something called the rational zeros theorem. And so your essential question is, how do I use that rational zeros theorem to find all the real zeros of a polynomial? And before we start talking about that theorem, I want to talk a little bit about the sets of numbers that we have, number sets. So this diagram is a pretty good diagram. It kind of tells you about how these things are set up. So our big type of numbers that we have are real numbers, and then each of these are a subset of the one before them. So our natural numbers, we write that, this is mathematicians being lazy, natural numbers is too hard to write apparently. We write that as an N with that like extra line through it. And natural numbers are also known as counting numbers. And basically they're all the whole numbers that you have that you would count with. So you start counting at 1, not 0, and then there's no negatives in there. Your integers are just counting numbers, and then you add in your negatives and you add in 0. Okay, so like that's kind of what that's showing here. We have some extra numbers in at the end, and then it's represented by a Z with that line through it. The next one are going to be rational numbers. Don't ask me why it's a Q. Mathematicians, again, weird, lazy. Rational numbers are basically fractions. And so when you're thinking about a rational number, you can have ones obviously like 2/3, -17/5. We could also have numbers like 0.75 because that's something I could rewrite as a fraction. But a rational number won't include things that are repeating decimals, or things not repeating decimals, things that don't repeat as a decimal, never-ending decimals. So something like √3. We don't know what the square root of 3 is. It never finishes, so that's not a rational number. Okay, pi. Pi is an irrational number as well. Okay, the big overarching set of these numbers, though, are called the real numbers, which includes things like pi or e or that square root of 3. So real numbers are basically anything that doesn't include that imaginary number I that you talked about in Algebra 2. Okay, and that's what we're looking at today. We're going to be finding fractional zeros, we'll be finding integer zeros, all that stuff. So let's talk about that zeros theorem we were talking about in the beginning. So this is the rational zero theorem. This theorem is going to find you possible rational zeros of a polynomial. So it's going to find you any of those zeros within that set of rational numbers. Again, it's possible. It's not going to tell you the answer. It may tell you one of the possible answers. And this is how you use it. The first thing that you're going to find is you're going to find P. And P represents the factors of the constant term. So remember, when you have a polynomial, you're going to have probably a number at the end that doesn't have an x next to it, and that would be your constant term, and you'd list out all the factors of that constant term. When you find Q, you're going to find the factors of the leading coefficient. So you're going to go find your exponent, the highest exponent you can, go look at the number in front, and that's where you're going to write down the factors of the leading coefficient. Once you have those two numbers, or those two sets of numbers, you then take all those P's and divide them by all those Q's, and that gives you every single possible answer to your problem. Okay, so let's do an example to kind of clarify what just happened in that theorem. We're going to find the possible rational zeros of this function. And the first thing I've got to do is I've got to list out my P and my Q. So my P are the factors of the constant term. My constant term is 8. So I'm thinking about anything that multiplies to get me 8. Well, I'd have 1, I'd have 2, 1 times 8, 2 times 4, and then 8. Okay, the hardest part about this one is you have to remember that technically I could have had a negative 1 also multiply to give me something. Negative 1 times negative 8 would have given me 8. So in order to make this process a little, less clunky, I'm just going to write a plus or minus in front of all the numbers I have. Okay, so you can have positive or negative ones of those. Then I'm going to go ahead and I'm going to find my Q. Zip. And that's going to be the factors of the leading coefficient. My leading coefficient is 4. And so I'm just going to, again, with a plus or minus, write down anything that would multiply to give me 4. And now that I have those two number sets, I am going to go write down all of the possible zeros by taking all my p values and dividing them by all my q values. Okay, this takes a little bit of time, but a lot of times things will show up twice, so you only have to write them once. And again, in the way of being lazy, I'm going to go ahead and write this as a number set and then put a plus or minus in front of it. You can write a plus or minus in front of every single one of your answers. That's fine. Okay, so I'm just going to go ahead and I'm going to use all my numbers here. So first I'm going to just start with taking this first p divided by this first q, and I'm going to go and list them all out. So I have 1 over 1. That would just simplify to be 1. 2 over 1 is 2. 4 over 1 is 4. 8 over 1 is 8. Okay, and then I'm going to go to my next one. I've done all of the this first one right here, right? So I'm going to now take 2 over 2. Well, that's just 1. I already have that one. Okay, I guess I need to take 1 over 1 too. But so you're going to see they're going to repeat. So now I also have 1 over 2. Sorry, I totally missed that one. 1 over 2. 2 over 2, 4 over 2 is going to be 2 again, and 8 over 2 is 4. So again, you're going to have ones that are going to repeat on you. Then I finally take that last q down here, so I'm going to have 1 over 4, don't have that one yet. 2 over 4 is 1/2, I already have that one. 4 over 4 is 1, 8 over 4 is 2, and I am done. Okay, so this is listing out all of the possible rational zeros of my solution here. So I could have any of these that might work out. This isn't telling me that all of these are going to work out. It's just telling me these are the ones that you want to focus on. So let's talk about how we're going to use this in the situation of finding real zeros. Okay? So when I look at this guy, they're going to ask me to factor something. Hold, please. Whew, sorry there. I looked and I was like, that is the same example we had last time. We're going to factor this thing instead. So if I had told you to factor this last week, you would have looked at this and said, I can't do anything with this. If I do this by grouping, I could take out an x squared, but then I wouldn't have matching terms here. So really what this theorem is going to do for us is it's going to help us figure out how to factor what was formerly unfactorable. Okay, so what I'm going to do here is I'm going to go ahead and list out all of the possible zeros, which would also be factors, using the rational zeros theorem. So we're going to go ahead and find those possible zeros. Okay, and so in order to do that, I'm going to, again, list out my factors of p and q just like we did in the first example. So for my p, I'm looking at my factors of my last term. So that would be plus or minus 1, plus or minus 2, factors of 6, plus or minus 3, and then plus or minus 6. Okay, then I look at my factors of q, which are going to be the numbers in front of, or the factors of the coefficient of that first term. So factors of 2 are just 1 and 2. So now when I list out my possible zeros, that would just be p over q. So I would do the same thing I just did in that other example, and I'd have plus or minus 1 over 1, 2 over 1, 3 over 1, and 6 over 1. And then I've used that one. Now I'm going to use a second set, so I'd have plus or minus 1/2, plus or minus 1, I already have it, plus or minus 3 over 2, and then plus or minus 6 over 2 is 3, I already have it. So these are all of the possible zeros that I could have for this function. And so what you're going to do here is, now that I know kind of where to start, instead of having to plug in every single number, I can just plug in one of these and kind of check. And so I'm going to pick one, and I'm going to be looking for something that has a remainder of 0 using synthetic division. So maybe I want to try 3. I like 3 today. I don't know. Okay, so if I take 3, one of my possible zeros, and I do some synthetic division with that factor. So again, list out your coefficients, and then you see what happens. So 2, 6, 7, 21. Except for yes, I got this. This is not what I wrote on my paper, so apparently I can't add again. So whatever. Then we'd have 8 here. 24, 30, which means my remainder is 30 here, which that is not a factor then, because it doesn't divide evenly into the function. Okay, so you're going to have to probably do a little bit of work here and go through and decide, is this guy actually a factor? So this is kind of the annoying part where there's not necessarily a specific process you go through. You kind of have to guess and check at this point. So on a test or a quiz, it's going to be pretty basic. There's not going to be, 12 zeros to choose from. And just for the purpose of time, I'm going to go ahead and be like, hey, look, 2 might work. And again, you do that synthetic division using the same function up here. 2, 4, 5, 10, -3, -6. That gave me that remainder of 0. I'm happy. That means that that factor that gives you the 0 is actually a factor. So one of my factors would be x minus 2. Then I can write down my remaining function that would have been there. So again, we'd have 2x squared plus 5x minus 3. And now I can look at this one and use a grouping method or factoring method I know, because that's just a regular trinomial. So I'm still going to have that factor of x minus 2, but then when I use my x, we can think about what's going to multiply to get me -6 and add to get me 5. Well, that would just be +6 and -1, and then I just factor that inside just like I did last week. And so, lots of parentheses going on here. And so you notice everything worked out for my 4-term grouping. So I have x minus 2 times, my first factor would be x plus 3, the one that matches, and then my leftovers. And I can't go any further with this. So that would be how I could fully factor that polynomial when I couldn't do it before. Also, if you look at these, that means that if I had tried to do this synthetic division with the answer of -3 or 1/2, it also would have worked out. So there's multiple ways to get this. Okay, let's do one more example of this theorem. And what we want to find are the real zeros of this polynomial. Okay, so the first thing we always try to do is factor it. And of course, this doesn't look like it's going to factor nicely, so I'm going to have to use my rational zeros theorem to think about possible factors before I can even get that far. So I'm going to go ahead and list out my p, which is my factors of 12. Yep, 4, because that's what multiplies by 3. And then I'm going to go ahead and list out my q, which is nice. The coefficient of that term is just 1. And so that means that my possible rational zeros are 1, 2, 3, 4, 5, 4, 6, and 12, positive or negative. Okay? And so in order to try to factor this, again, you're just going to take your possible factors and try to do synthetic division with them. Again, for the sake of time, I'm going to go ahead and tell you that 3 does work. But if you had to do this, again, just make a process for yourself. Try 1 and then try -1, and try 2 and try -2. On a test, it wouldn't be too bad. But if I go ahead and I do synthetic division with 3, it's going to get me the rest of that polynomial. -6, -4, 0. And so good, I have a remainder of 0, and that would mean that my first factor would be x minus 3. Remember, we have to change the sign. And then we'd have 1x squared minus 2x minus 4. Now before, my second trinomial did factor, and it made something nice and blah, 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 blah. So I do know one of my zeros is 3, but I don't know what the 0 is here. And there are 2 ways you can do this in order to figure out what these zeros are. Remember, we're going to set this equal to 0 and see what those factors are. You could complete the square, okay, or you can use quadratic formula. And I tend to go to the quadratic formula just because it'll always work no matter if it's imaginary or not. So if you remember what the quadratic formula is, you can always sing your song. X equals -b plus or minus the square root of b squared minus 4ac all over 2a. And then you just plug in what you know. So we'd have a, the coefficient right here is 1, b is -2, and c is -4. And plug that in there. So we'd have -2, which would be 2, plus or minus b squared would be negative 2 squared, okay, minus 4 times a times c all over 2 times 1. Okay, and then you just got to simplify. So this is x equals 2 plus or minus the square root. We'd have 4 and then plus 16 because those 2 would go away. So 4 plus 16 is 20 all over 2. I made that line way too long. And then you go ahead and you simplify this down a little bit. And so I know that the square root of 20 can simplify that. If I simplify that radical down, that would be the square 2 times the square root of 5. And the reason that we want to do this is because I would like to make this simpler. I want to cancel these 2's out. But remember, you cannot just cancel this 2 and then leave the root 20. You have to make sure it goes into everything on the top. And so this one right here, now I can cancel out all these 2's. And my other real 0 would be 1 plus or minus the square root of 5. I wouldn't have found that with my rational zeros theorem because it only finds rational numbers. So if I want to find my final answer, all of my real zeros, we had that one I found first, that was a nice rational number, which was 3. Then I had 1 plus the square root of 5, and I had 1 minus the square root of 5. That is all the places that my polynomial is crossing the x-axis. Okay, and that is all I've got for you. Again, the reason that we have that rational zeros theorem is so that we can try to factor something that didn't seem factorable at first, and then go ahead and, if we need to, use the quadratic formula or complete the square to finish solving my problem. Have a great night.